There is an equation written on the wall of Paul Dirac's old office in Cambridge. It fits comfortably in a single line, the kind of line you might mistake for a note someone scrawled before leaving the room. But that line, written down for the first time in 1928, did something no equation had done before. It looked at the electron and told us what the electron actually was, structurally, completely. And in doing so, it revealed the possibility of antimatter, and cracked open a door that physics is still walking through. That equation is the Dirac equation. You have almost certainly never thought about it. Most people have not. It lives in the graduate textbooks, behind the vocabulary of quantum field theory and relativistic mechanics, behind years of mathematics that most people never encounter. And yet everything it describes is happening inside you right now. Every electron in every atom in every cell of your body is behaving according to what Dirac wrote down nearly a century ago. Think about what your hand feels like when you press it against a table. There is a resistance there, a firmness. The table does not let your hand pass through it. You have felt this 10,000 times, and it has never once struck you as strange. But it is strange. The atoms in your hand and the atoms in the table are almost entirely empty space. If you scaled a single atom up to the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be specks somewhere near the outer seats, with nothing between them but void. Two objects made almost entirely of nothing pressing against each other and producing the sensation of solid resistance. The ordinary world is built on something deeply counterintuitive, and the electron is at the center of it. The electron is responsible for the chemical bonds that hold molecules together, for the way light interacts with matter, for electricity moving through a wire, for the solidity you feel when you sit in a chair. It is the most consequential particle in the daily texture of human experience. And for decades after its discovery, physicists could not write down an equation that described it correctly. Every equation they tried was missing something the electron kept insisting on in experiments that nobody could explain from first principles, a kind of internal rotation that had no analogue in ordinary experience, a magnetic behavior that no classical picture could reproduce, a stubbornness about its own identity that sat just outside the reach of every theoretical framework until Dirac. What did Dirac actually do? Why did his equation succeed where every previous attempt had fallen short? And what did it reveal about reality that nobody had expected or gone looking for? Those are questions with a descent inside them, a step-by-step uncovering of why the electron is the way it is, why the universe required a particular kind of mathematics to describe it, and why that mathematics quietly predicted the existence of something no one had ever seen before, something that turned out to be real. How does an equation written on a single line end up describing the deep structure of matter? And why did following the logic of that equation lead Dirac somewhere that should have been impossible? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you're watching from, and if there is something about the universe you find yourself wondering about, let me know in the comments. I always wonder which curiosities other people carry around with them, and who knows, it might become one of the next topics we will explore. For now, let's get back to that question. The place to begin is with the electron itself, with what was known about it before 1928, and with why that knowledge kept producing the wrong answers. In 1897, a physicist named J.J. Thomson was running electrical current through a glass tube with almost all the air sucked out of it. What came out of the metal electrode inside that tube was a beam of something. It bent when Thomson held a magnet near it. It bent the same way regardless of what metal the electrode was made from. Whatever it was far lighter than any atom ever measured. Thomson had found the electron, a particle so small it lived inside atoms, a particle that came out of matter but was smaller than any piece of matter anyone had ever identified. For a while, the electron seemed straightforward, a tiny ball of negative electric charge, small, fast, and simple, the kind of object classical physics was built to handle. You could imagine it like a miniature marble, spinning through space, orbiting the nucleus the way a planet orbits the sun. That picture felt satisfying. It had the clean geometry of something a person could hold in their mind. But the electron refused to behave like a marble. The first sign of trouble came from the way electrons inhabit atoms. If an electron were truly like a planet orbiting a star, it would continuously radiate energy as it curved through space. A charged particle moving in a circle loses energy by emitting light. A real orbiting electron should spiral inward within a fraction of a second, collapsing into the nucleus and destroying the atom. Every atom in the universe should have collapsed long ago. The fact that you are reading this, that matter exists in stable forms at all, meant the classical picture was missing something fundamental. Then came the results from experiments firing light at metal surfaces. When light hits a metal, electrons get knocked loose. Classical physics predicted that brighter light would knock electrons out with more energy. What actually happened was that the energy of the ejected electrons depended on the color of the light, its frequency, not its brightness. Dim violet light ejected electrons with more energy than intense red light. The energy came in discrete packets tied to frequency. Einstein explained this in 1905 by treating light itself as composed of discrete chunks, photons. The electron was interacting with light in a way that had no classical explanation. Then came something stranger still. Fire a beam of electrons at a barrier with two narrow slits in it and collect them on a screen behind. Classical thinking says each electron goes through one slit or the other and lands somewhere on the screen. What you get instead is an interference pattern, alternating bands of many electrons and few electrons. The same pattern you would get from waves passing through two openings and overlapping on the other side. The electron, a thing with mass and charge and a definite location when you measure it, travels like a wave when you leave it alone. The marble picture was not just incomplete, it was the wrong kind of picture entirely. The electron occupied a strange middle territory. It had particle properties, it had wave properties, it had a charge and a mass you could measure. It also spread itself across space in a way that defied any image of a small solid object. Classical physics had no framework for something like that. The equations built to describe billiard balls and planets simply did not apply. A new framework was needed, one that could hold the wave and the particle in the same description without contradiction. That framework arrived in the 1920s, and it went by the name of quantum mechanics, and its first serious attempt to describe the electron produced an equation that was powerful, elegant, and quietly incomplete in a way that would take Dirac to resolve. In 1926, Erwin Schrödinger wrote down an equation that did something genuinely new. It treated the electron as a wave, a spread-out, undulating thing that occupied a region of space rather than a fixed point. The equation described how that wave evolved over time, how it stretched and contracted and shifted as the electron moved through its environment. And when you fed the right conditions into it, when you asked it what wave could exist around a hydrogen nucleus, it spat back exactly the right energy levels. The discrete steps that experiments had been measuring for decades without any theoretical explanation. The equation worked. Think of the electron's wave like the vibration pattern on a drum skin when you strike it. The drum does not vibrate randomly. It settles into specific patterns determined by its size and tension. Each pattern has its own frequency. Each frequency corresponds to a specific energy. The electron around a nucleus behaves the same way. Only certain wave patterns fit around the nucleus without cancelling themselves out. Those patterns correspond to the discrete energy levels of the atom. Schrödinger's equation was the rule that determined which patterns were allowed. This was a profound step. It gave quantum mechanics a concrete mathematical engine, a procedure you could follow to calculate the behavior of electrons in atoms, in molecules, in any system you could describe clearly enough to feed into the equation. Chemistry, which had been largely an experimental science built on accumulated observation, suddenly had a theoretical foundation it could calculate from. The periodic table, the behavior of chemical bonds, the way atoms combined into molecules, all of it became derivable in principle from a single equation governing a wave. And for the electrons in ordinary atoms moving at ordinary speeds, the Schrödinger equation was extraordinarily accurate. It remains the workhorse of chemistry and materials science to this day. Every calculation predicting how a drug molecule binds to a protein, how a semiconductor conducts electricity, how a solar cell absorbs light, runs on the framework Schrödinger built. But there was a condition buried in all of that success, a condition that held as long as you did not look too carefully at electrons moving very fast. The Schrödinger equation was built on the classical relationship between energy and momentum, the relationship that holds when speeds are small compared to the speed of light. At those speeds, the equation was accurate, but electrons in certain environments move fast. Electrons close to heavy atomic nuclei, where the electrical pull is strongest, move at speeds that are a significant fraction of the speed of light. And at those speeds, the classical energy-momentum relationship that Schrödinger's equation was built on begins to give the wrong answer. It is like using a map drawn for flat terrain to navigate a mountain range. For gentle hills, the flat map works well enough. The errors are small and manageable. But as the terrain gets more extreme, the errors compound. The map and the territory increasingly disagree. You can still use the map, but you should not trust it completely. The Schrödinger equation had the same limitation. It was a flat map in a curved landscape, accurate enough for slow electrons, but quietly accumulating errors as speeds rose. And there was a deeper problem than just accuracy. The equation treated time and space differently. In Schrödinger's framework, time was a parameter that the equation evolved through, while space was the stage on which the wave played out. Special relativity had shown in 1905 that time and space were not separate stages. They were woven together into a single fabric. Any equation that treated them differently was not just approximately wrong at high speeds. It was structurally misaligned with the geometry of reality. Fixing that misalignment was the problem Dirac set out to solve, and the way he approached it was unlike anything his contemporaries were trying. In 1905, Albert Einstein published a paper that quietly dismantled the stage on which all of physics had been performed. Before that paper, space and time were separate. Space was the room. Time was the clock on the wall. They were independent. They did not influence each other. A meter was a meter and a second was a second, regardless of how fast you were moving or where you were standing. That was the assumption every equation in physics had been built on for 2 centuries. Einstein showed the assumption was wrong. Space and time were not separate. They were aspects of a single unified thing, a 4-dimensional fabric that physicists came to call space-time. And the geometry of that fabric had consequences that felt deeply strange when encountered for the first time. A clock on a fast-moving train ticked slower than a clock sitting still. A ruler on that same train was shorter along the direction of motion than an identical ruler at rest. These were not illusions or measurement errors. They were real geometric features of the world that became significant as speeds approached the speed of light. Think of it like this. Imagine you are walking across a town square diagonally. You are covering distance in two directions simultaneously, forward and sideways. The faster you move sideways, the less of your total speed is going forward. Space and time work similarly. The faster an object moves through space, the slower it moves through time. Speed through space and speed through time are connected, drawing from the same total. You cannot change one without affecting the other. For everyday objects moving at everyday speeds, this effect is so tiny it is completely undetectable. A car, a plane, even a spacecraft moves slowly enough compared to light that the relativistic effects are negligible. The flat map works fine for gentle hills, but electrons are not cars. Near a heavy nucleus, an electron can move at a substantial fraction of the speed of light. At those speeds, the relativistic effects are real, measurable, and chemically significant. The color of gold, the behavior of mercury at room temperature, the way certain heavy atoms bond, all trace back to relativistic effects on their electrons. The geometry of space-time reaches directly into the texture of the material world, so any equation claiming to describe the electron completely had to be built on relativistic foundations. It had to treat space and time on equal footing. It had to respect the geometry Einstein had uncovered. The Schrödinger equation did none of those things. It was a pre-relativistic equation patched onto a quantum mechanical framework. Useful, accurate at low speeds, but architecturally mismatched with the actual structure of space-time. Physicists knew this. The attempt to fix it was already underway before Dirac arrived at the problem. Two physicists, Oscar Klein and Walter Gordon, had written down a relativistic wave equation in 1926. It treated space and time symmetrically. It was built on the correct relativistic relationship between energy and momentum. On the surface, it looked like exactly what was needed. But when physicists examined its solutions carefully, something went wrong. The equation produced probabilities that could go negative. A probability is a number between 0 and 1. It measures how likely something is to occur. A probability of 0 means impossible. A probability of 1 means certain. A negative probability means nothing. It is not a small probability. It is not an unlikely outcome. It is a mathematical object with no physical interpretation whatsoever. An equation that produces negative probabilities is an equation that has lost contact with physical reality somewhere in its structure. The Klein-Gordon equation was relativistic, but it was describing something other than a single electron moving through space. It was, as physicists would later understand, actually describing a different class of particles entirely. For the electron, it was the wrong tool. The problem of writing a relativistic quantum equation for the electron was still open, and that is the problem Dirac sat down with. An equation that needed to be quantum mechanical and relativistic simultaneously, that needed to produce sensible probabilities at every step, and that needed to describe the electron as it actually behaved in experiments. The constraints were precise, the solution was not obvious, and the path Dirac took to find it was one of the most striking examples of mathematical reasoning in the history of physics. Paul Dirac was 25 years old when he sat down with this problem. He was known among his colleagues for a particular style of thinking, quiet, precise, almost mechanical in its patience. He did not guess at equations and check whether they worked. He followed the logic of what an equation was required to be, and let that logic tell him what form it had to take. The distinction matters because it meant the Dirac equation was not a creative leap, so much as an inevitable conclusion. Given the constraints, only one answer was consistent. Dirac found it by refusing to accept anything less. The starting point was a requirement about probability. In quantum mechanics, the wave function is everything. It is the mathematical object that encodes all the information about a particle, where it might be, how fast it might be moving, what energy it might have. The wave function spreads across space, and its square at any point tells you the probability of finding the particle there. For that to make sense, the total probability of finding the particle somewhere has to equal 1. The particle exists. It is somewhere. The probabilities across all of space must add up to certainty. This requirement has a name. Physicists call it unitarity, and it places a hard constraint on the form any valid quantum mechanical equation can take. The equation must be structured in a way that preserves this total probability as time passes. As the wave function evolves, the sum of all probabilities must remain exactly 1. An equation that allows that sum to drift, to grow larger or shrink or go negative, is an equation that has allowed the particle to multiply, vanish, or become a fiction. The Klein-Gordon equation failed this requirement because it was second order in time. That is a technical way of saying that to predict the future state of the wave function, you needed to know both its current value and how fast it was currently changing. 2 pieces of initial information instead of 1. This doubling introduced solutions with the wrong mathematical character, solutions that behaved in ways inconsistent with sensible probabilities. The equation was relativistic, but it was not quantum mechanical in the right sense. Schrödinger's equation was first order in time. 1 piece of initial information, 1 value of the wave function now, and the equation tells you the value a moment later. That structure was what made probabilities well behaved. That structure was what Dirac decided to preserve. So the constraint was this. The new equation had to be first order in time, and because relativity required space and time to be treated symmetrically, it also had to be first order in space. Every spatial direction on equal footing with time. The equation had to be linear in all its derivatives, time and space together, or the symmetry Einstein demanded would be broken from the start. This sounds like a reasonable requirement until you try to satisfy it. The relativistic relationship between energy and momentum involves squares. Energy squared equals momentum squared plus mass squared, multiplied by the appropriate constants. That is the relativistic constraint every valid equation must encode. But squares are second order, and Dirac needed everything first order. Imagine trying to take the square root of a sum. The square root of 9 plus 16 is 5, but the square root of 9 plus the square root of 16 is 7. Taking a square root does not distribute across addition the way multiplication does. The mathematics resists. You cannot simply reach in and extract a first-order equation from a second-order relationship by ordinary algebra. Dirac's insight was that the resistance could be overcome if you allowed the coefficients in the equation to be something other than ordinary numbers. If the coefficients were objects that obeyed specific algebraic rules among themselves, rules that ordinary numbers do not obey, then the square root could be taken in a generalized sense. The equation could be made first order without abandoning the relativistic energy-momentum relationship. Those objects existed. They were a known piece of mathematics called matrices, arrays of numbers that combine according to their own rules, rules where the order of multiplication matters, where multiplying A by B can give a different result than multiplying B by A. Dirac found a specific set of 4 matrices that satisfied exactly the conditions his constraint demanded, and when he assembled them into an equation, something unexpected came out the other side. The equation worked, but it described something larger than a single electron, and the extra content it carried was about to cause a crisis that would take years to resolve. When Dirac assembled his matrices into the equation and looked at what it described, the first thing he noticed was that the wave function had changed shape. In Schrödinger's framework, the wave function was a single number at each point in space. One value, one piece of information per location telling you the probability amplitude of finding the electron there. Simple, clean and sufficient for a slow-moving electron in an atom. The Dirac equation required 4 numbers at each point in space, a wave function with 4 components stacked together, evolving simultaneously, each influencing the others as time moved forward. The equation did not describe a single wave spreading through space. It described 4 interlocked waves moving together as a unit, a mathematical object physicists call a spinor, something richer and more structured than anything the Schrödinger equation had needed. Think of it like the difference between tracking the temperature in a room and tracking the full weather in a region. Temperature is one number at each location, but weather involves wind speed, wind direction, humidity, and pressure simultaneously. Each quantity is real. Each influences the others. To describe the weather honestly, you need all of them together. Dropping any one of them gives you a picture that is not just incomplete, but actively misleading. The Dirac wave function was like that. 4 components, each necessary, each connected to the others, none of them meaningful in isolation. The natural question was what the 4 components meant physically. 2 of them were immediately recognizable. They corresponded to 2 distinct internal states of the electron, 2 orientations of something the electron carried internally that experiments had already detected but never explained from first principles. That property was spin, the idea that the electron behaved as though it were rotating about an internal axis, producing a tiny magnetic effect that showed up in spectroscopic measurements. Before Dirac, spin had been inserted into quantum mechanics by hand. Physicists knew electrons had it because experiments demanded it, but no one had derived it from deeper principles. No one had shown why the electron had to have spin. It was an observed fact bolted onto the theory rather than emerging from it. Here, it simply fell out. The structure of the equation, forced entirely by the requirements of relativity and unitarity, automatically produced 2 internal states, 2 possible orientations. The spin of the electron was not an assumption Dirac made. It was a consequence he discovered after the equation was already written. The mathematics had known about spin before the physicist did. That was striking enough on its own. But it accounted for only 2 of the 4 components. The other 2 remained, and they were harder to interpret. Those 2 extra components corresponded to solutions where the energy of the electron was negative. In the framework of the equation, for every state of positive energy describing an electron moving in a particular way, there existed a corresponding state of negative energy, a mirror image solution carrying the same momentum but with its energy flipped below 0. In classical physics, this would be straightforwardly dismissed. Negative energy is not a physical thing. An object cannot have less energy than nothing. A ball rolling across a floor cannot have a negative kinetic energy. The negative solutions would be thrown out as mathematical artifacts with no physical meaning, the way you sometimes get negative distances as solutions to geometry problems, and simply discard them, because distances cannot be negative. But quantum mechanics does not allow that kind of casual dismissal. The equation was not producing negative energy as an occasional artifact. It was producing it systematically. For every positive energy solution, there was a corresponding negative energy partner. The negative solutions were as mathematically valid as the positive ones. Discarding them by hand would break the internal consistency of the framework. It would be like building a bridge and quietly ignoring the fact that half the load-bearing calculations were giving you negative forces. The mathematics was trying to say something. The question was what? And underneath that question was a more unsettling one. If negative energy states existed and electrons could fall into them, what was stopping every electron in the universe from cascading downward into lower and lower energy states forever, releasing infinite energy as it fell and making stable matter impossible? Picture a ball sitting on a staircase that descends forever. There is no bottom step. The staircase just keeps going down. Gravity pulls the ball downward, and there is nothing to stop it. Given any nudge at all, the ball rolls off the step it is on and falls to the next one, then the next, then the next, endlessly. A system like that cannot have stable resting states. Everything just falls. This was the problem Dirac was staring at. The negative energy solutions were not a minor inconvenience sitting at the edge of the theory. They were a structural feature of the equation. Every positive energy state describing a real electron had a corresponding negative energy mirror below it. And in quantum mechanics, particles do not stay put unless something forces them to. An electron sitting in a positive energy state could, in principle, emit a photon and drop into a negative energy state, then emit another photon and drop further, then further again. The energy released in each drop would go somewhere, carried away as light, and the electron would keep falling because the staircase had no floor. If this were allowed to happen, the universe would be catastrophically unstable. Every electron in every atom would drain itself downward into negative energy, flooding space with radiation and leaving behind nothing recognizable as matter. Atoms would dissolve. Chemistry would cease. The fact that you are sitting somewhere stable reading this was itself evidence that something was preventing the collapse. Something was blocking the descent. Dirac found the answer by thinking about a completely different physical system. A metal. In a metal, the electrons do not all pile into the single lowest energy state available to them. They fill up the available states one by one, from the lowest upward, stacking into higher and higher energy levels as each lower level becomes occupied. This happens because of a rule that governs electrons specifically, a rule that says no two electrons can occupy exactly the same quantum state simultaneously. Each state holds one electron and one electron only. Once a state is filled, it is closed. No additional electron can enter it regardless of how energetically favorable it would be to do so. That rule is the Pauli exclusion principle, and Dirac recognized that it was the missing piece. If every negative energy state in the universe was already occupied, already filled with an electron, then the Pauli exclusion principle would slam the door on any further descent. A positive energy electron trying to drop into a negative energy state would find that state already taken. Every negative energy slot full, every downward step blocked. The staircase still descended forever, but every step was already occupied. The ball had nowhere to fall. This was Dirac's proposal. The vacuum, the state of lowest energy that we call empty space, was not actually empty. It was a sea, an infinite ocean of electrons packed into every available negative energy state, filled completely and uniformly throughout all of space. What we called empty space was in reality a kind of dense, invisible medium, a filled background against which the positive energy electrons we observed were floating like air bubbles in water. The image is striking, but it immediately raises its own questions. If the vacuum is full of electrons, why do we not detect them? Why does empty space not feel heavy? Why does it not scatter light or pull on charged objects, or make its presence known in any of the ways a room full of electrons should? The answer Dirac gave was that a perfectly uniform filled sea produces no net force on anything, no gradients, no variations, nothing to push against. You do not feel the atmosphere pressing down on you from above because air pressure pushes equally from all directions and the net effect cancels. In the same way, a perfectly filled uniform sea of negative energy electrons exerts no net electromagnetic force, produces no observable density, registers on no instrument. It is present but invisible because it is perfectly homogeneous, until something disturbs it. And when something did disturb it, Dirac realized, the disturbance would look exactly like a new kind of particle, one that had never been observed, one that the theory was now predicting must exist. The Dirac sea was a radical proposition. Empty space was full. The vacuum was not a void, but a medium, packed uniformly with electrons occupying every available negative energy state. Invisible because it was perfectly uniform, present everywhere but detectable nowhere under ordinary conditions. Think of it like the floor of an ocean. If the water above you is completely still and perfectly uniform in every direction, you feel no current, no pull, no pressure difference from any side. The water is there, but its presence registers as nothing. The Dirac sea worked the same way, a perfectly filled background that physics happened on top of, contributing nothing to any measurement as long as it remained undisturbed. But oceans can be disturbed, and so could the sea. If a photon carrying enough energy struck the sea, it could do something specific. It could knock one of the negative energy electrons upward into a positive energy state. The electron would emerge into the observable world as a real particle, detectable, measurable, behaving exactly like every other electron. That part was straightforward. What Dirac focused on was what happened in the sea itself. Where the electron had been, there was now a gap, an unoccupied state in the otherwise perfectly filled background. A hole. That hole was not nothing. A missing negative charge in a sea of negative charges behaved from the outside exactly like a positive charge. A missing negative energy in a sea of negative energies behaved like a positive energy. The hole had the mass of an electron because it was shaped by the electron-sized space it occupied. It had opposite electric charge because its absence from the sea of negative charge registered as a positive charge to everything around it. The hole behaved exactly like a particle, a real, observable, positively charged particle with the mass of an electron. Something that could move through space, interact with light, scatter off other particles. An absence that had all the properties of a presence. Dirac was looking at the first theoretical prediction of antimatter, and he arrived there not by searching for it, but by following the logical consequences of an equation he had been forced to write by the demands of relativity and quantum mechanics combined. The hole in the Dirac sea was not a vague theoretical suggestion, it was a precise prediction. Whatever filled that gap would have the mass of an electron, because the hole was exactly electron-shaped. It would carry positive electric charge, because its absence from a uniform sea of negative charge registered as a positive to everything surrounding it. It would respond to magnetic fields, scatter off other particles, and leave tracks in a detector. It was, in every measurable sense, a particle, one that had never been observed but whose properties the equation specified exactly. Dirac initially resisted the conclusion. The idea that empty space was a sea and that holes in that sea were particles felt too strange, even for a theory already full of strange things. His first instinct was to identify the hole with something already known. The only positively charged particle in the available inventory at the time was the proton. Dirac wondered briefly whether the hole might be the proton. It could not be. The proton is nearly 2,000 times heavier than the electron. The hole had to have exactly the electron's mass because the gap it represented was exactly electron-sized. A hole shaped by the absence of an electron could not weigh 2,000 times more than an electron, any more than a footprint in sand could weigh more than the foot that made it. The identification failed immediately on quantitative grounds. What the equation was describing was something else entirely, a particle that matched the electron in every property except the sign of its electric charge, a mirror image particle, something the universe had apparently kept hidden until a 25-year-old physicist followed the logic of an equation to its conclusion and found it waiting there. Dirac published the prediction in 1931. He called it the anti-electron, a positively charged particle with the electron's mass, the electron's behavior, and a relationship to the electron so precise and symmetrical that the two particles were essentially reflections of each other across the boundary of electric charge. The response from the physics community was cautious. A prediction is only as credible as the framework it comes from, and the Dirac sea was a deeply unusual framework. An infinite, invisible ocean filling all of space was not the kind of physical picture that inspired immediate confidence. The prediction sat in the literature, acknowledged but unconfirmed, while experimentalists continued their work without specifically searching for something most of them considered unlikely. Then the universe offered the answer without being asked. In 1932, Carl Anderson was studying cosmic rays, high-energy particles raining down from space, colliding with the atmosphere, and producing showers of secondary particles that Anderson was tracking inside a cloud chamber. A cloud chamber is a container filled with supersaturated vapor that reveals the paths of charged particles as thin trails of condensation, the way a jet aircraft leaves a white line across a clear sky. Each trail curves in a magnetic field by an amount that reveals the particle's charge and momentum. Anderson saw a trail that curved the wrong way. Every electron he had ever tracked curved in one direction under the magnetic field. This trail curved in the opposite direction, the way a positively charged particle would curve, but with a curvature that matched the electron's mass exactly. A proton would have curved far less sharply at that momentum. Whatever made this track was light, like an electron, but carried positive charge. Anderson called it the positron. He had not been looking for it. He had not read Dirac's prediction carefully enough to know he should be looking for it. He found it because the universe was producing it constantly in cosmic ray showers, and he happened to be watching closely enough to see. When the physics community connected Anderson's positron to Dirac's anti-electron, the implications settled in slowly and then all at once. An equation written from pure theoretical constraint, from the demand that quantum mechanics and relativity be reconciled honestly, had predicted the existence of a particle before any human had detected it. The equation had seen further than the experiments. The mathematics had described something real before the instruments caught up, and if the electron had an antimatter partner, the question immediately arose whether every other particle did too, whether the universe contained a complete mirror inventory, whether every piece of matter had a corresponding piece of antimatter waiting to be found. The answer, confirmed by decades of subsequent experiment, was yes. Before Dirac, spin was an awkward addition to quantum mechanics. Physicists knew electrons had it because experiments demanded it. When a beam of electrons passed through a magnetic field, it split into two distinct beams rather than spreading into a continuous fan. Something about the electron was producing a tiny magnetic effect that could point in one of two orientations relative to the field, up or down, nothing in between. That binary behavior had no classical explanation. A spinning, charged ball would produce a magnetic effect, but it could point in any direction, not just two. The electron was doing something that had no analogue in ordinary rotating objects. Wolfgang Pauli had incorporated spin into quantum mechanics in 1927 by simply declaring it. He added two components to the wave function, one for each orientation, and wrote down rules for how they behaved. The rules worked, the predictions matched experiments, but the justification was essentially observational. Spin was in the theory because experiments said it had to be. It was bolted on rather than derived, a fact about electrons that quantum mechanics accommodated without explaining. Then Dirac wrote his equation, and spin fell out on its own. The four-component wave function that the equation required automatically contained two components corresponding to the two spin orientations of the electron. They were not inserted. They were not assumed. They emerged directly from the algebraic structure of the matrices Dirac had been forced to use in order to satisfy the requirements of relativity and unitarity. The same mathematical move that made the equation relativistically consistent was the move that produced spin as an automatic consequence. This was a qualitative shift in what spin meant. Before Dirac, it was an observed property that theory accommodated. After Dirac, it was a necessary consequence of combining quantum mechanics with special relativity. Any particle described by a relativistic quantum equation of the type Dirac wrote would have to have spin. It was not a peculiarity of the electron. It was a structural feature of what it meant to be a relativistic quantum mechanical particle with half-integer spin. The universe was not strange for giving electrons spin. It would have been strange if it had not. Spin made the electron behave like a tiny magnet. A spinning charged object generates a magnetic field, the way a current loop generates a magnetic field, and the electron's spin produced exactly that effect. The strength of that magnetic effect relative to the electron's spin is called the magnetic moment, and before Dirac there was a classical formula for estimating it. The formula gave a number. Call it 1 unit of magnetic strength for 1 unit of spin. That was the classical expectation. What experiments actually measured was twice that. The electron's magnetic moment was 2 units for 1 unit of spin, a factor of 2 larger than any classical picture predicted. Physicists call this factor the G factor, and its value of 2 for the electron was an experimental result that sat in the literature without theoretical explanation, the same way spin itself had sat without explanation before Dirac. When physicists worked through the predictions of the Dirac equation, they found the G factor waiting inside it. The equation produced a magnetic moment exactly twice the classical expectation, a G factor of precisely 2. No assumption required, no parameter inserted by hand. The same matrices that produce spin also produce the correct magnetic strength automatically. Think of it like measuring a shadow and using that measurement to deduce not just the height of the object casting it, but also its exact weight and color, properties you had no reason to expect the shadow to reveal. The Dirac equation was doing something similar. It was producing correct answers about properties that nobody had told it to address. The story did not stop there. Later refinements using quantum electrodynamics, the fuller theory that grew out of Dirac's framework, pushed the prediction of the G factor to extraordinary precision. The theoretical prediction and the experimental measurement of the electron's magnetic moment now agree to more than 10 decimal places. It is the most precisely verified prediction in the history of science, a number that theory and experiment arrive at independently and find to be identical far beyond any reasonable coincidence. That level of agreement does not happen by accident. It is the signature of an equation that is describing something real with extraordinary fidelity. The Dirac sea left a permanent mark on how physics thinks about empty space. Before Dirac, the vacuum was simple. Remove all the particles from a region of space, cool it to absolute zero, shield it from every external influence, and what remains is nothing, a true void, the baseline of reality against which everything else is measured. The Dirac equation made that picture untenable. If the negative energy states had to be filled to prevent electrons from cascading downward forever, then the vacuum was not empty. It was the most populated place in the universe. Every negative energy state occupied, an infinite invisible medium present everywhere simultaneously. What we called empty space was actually the ground floor of a filled structure, the lowest possible configuration of the electron field, brimming with activity that ordinary instruments could not detect because it was perfectly uniform. This was uncomfortable. An infinite sea of electrons filling all of space carried infinite charge and infinite energy. Those infinities were deeply problematic mathematically. Physicists developed techniques to subtract them out, to measure only differences from the vacuum baseline rather than absolute values, and those techniques worked well enough to make predictions. But the infinities never fully disappeared. They were managed rather than resolved. What survived the discomfort was the core insight. The vacuum was a physical object with structure. It was not nothing. It had a ground state that could be probed, disturbed, and measured indirectly. And experiments confirmed this. The Casimir effect is one of the clearest demonstrations. Place two uncharged metal plates extremely close together in what appears to be empty space, and they attract each other. The attraction arises because the vacuum between the plates is slightly different from the vacuum outside them. The confined geometry restricts which fluctuations can exist between the plates compared to outside, creating a pressure difference that pushes them together. Empty space between two plates pushes them toward each other. The vacuum is doing mechanical work. The ground state of reality is not nothing. It is a structured, energetic medium that Dirac's equation was the first to demand. The four-component wave function of the Dirac equation was always pointing towards something larger than a single electron. A single particle moving through space does not naturally require four interlocked components evolving together. That richness was a signal. The equation was not just describing one electron, it was describing a field, a structure spread across all of space from which electrons and positrons could emerge and into which they could dissolve. Think of a guitar string. When you pluck it, the string vibrates and produces a note. The note is not a separate thing sitting inside the string waiting to be released. It is a pattern of vibration in the string itself. Remove the string, and the note cannot exist. The string is the fundamental thing. The note is what the string does when disturbed. The electron field works the same way. It fills all of space the way the guitar string spans the length of the instrument. An electron is not a tiny ball sitting inside the field. It is a localized vibration of the field itself, a ripple, a disturbance that travels through the medium, carrying energy and momentum and charge, behaving in every way like a particle, because that is what a stable, localized ripple in a quantum field looks like from the outside. The Dirac equation, reinterpreted in this light, was not an equation for a particle, it was an equation for a field, and that reinterpretation resolved the most uncomfortable feature of the Dirac sea. The sea was not literally an infinite ocean of actual electrons crammed into negative energy states. It was a way of describing the ground state of the electron field, the state the field settled into when no disturbances were present. Particles were excitations above that ground state. Antiparticles were disturbances of a different kind. Both emerged from the same underlying field. This reinterpretation became quantum field theory, the framework that replaced both the Dirac C-picture and the single particle picture with something cleaner and more powerful. Every fundamental particle in nature is, in this framework, a ripple in its own field. Photons are ripples in the electromagnetic field, quarks are ripples in the quark field, and electrons are ripples in the Dirac field, governed at the deepest level by the equation Dirac wrote in 1928. Dirac sat down with a specific and narrow problem: how to write a quantum mechanical equation for the electron that respected the geometry of space-time. The problem had clear constraints. The solution had to be first order in time and space. It had to preserve probability. It had to encode the relativistic relationship between energy and momentum. Those were the walls of the room he was working in. He found the only equation that fit inside those walls. And what came out the other side was not just a better description of the electron. It was a set of revelations that nobody had gone looking for. Spin, which had been bolted onto quantum mechanics by hand, emerged as a structural necessity. The magnetic moment of the electron, which had sat in experimental data without explanation, came out of the mathematics automatically and matched measurements to extraordinary precision. A new particle, opposite in charge but identical in every other property to the electron, was predicted years before any instrument detected it. And the vacuum, the baseline of reality that physics had always treated as passive and empty, turned out to be a structured medium with mechanical properties that experiments could measure directly. None of these were inputs, they were outputs. Dirac had not set out to discover spin or predict antimatter or redefine the vacuum. He had set out to write a consistent equation. The equation then told him things about reality that he had not asked it. That is what makes the Dirac equation unusual, even among the great equations of physics. Most equations describe what we already know in a more precise or general form. They organize existing knowledge into a tighter framework. The Dirac equation did that, but it also reached beyond what was known and came back with things that were true before anyone had confirmed them. It was not a summary of observations, it was a window. What the equation actually says, stripped of the mathematics, is something like this. A particle that exists in space-time, that has mass, that behaves quantum mechanically, and that travels at speeds where relativity matters, cannot be what classical physics imagined. It cannot be a simple spinning marble with a charge attached. It must have an internal structure with 4 components. It must have a partner of opposite charge. It must live inside a field whose ground state is not empty. And the space it inhabits must be a physical object in its own right, capable of being disturbed, capable of doing work, capable of producing particles from apparent nothingness when enough energy is applied. The electron did not turn out to be simple, but the equation describing it turned out to be inevitable. Given the constraints, nothing else was possible. The universe, in order to contain something as ordinary as the electron, had to be structured in a way that made antimatter necessary, made spin unavoidable, and made the vacuum a physical medium rather than an absence. Dirac found all of that by refusing to accept an equation that did not hold together completely. The reward for that refusal was a single line on a wall in Cambridge that contains, quietly and precisely, some of the deepest things physics has ever said about the structure of reality.